All right, hi everybody. This is Mr. Mellinger for your AP Chemistry class. This is day 2. The date is January 29th, 2019, and we're going to work on your notes that you will bring into class on Wednesday, and we'll talk about these subjects. I will tell you very explicitly when I want you to take a note on something, and otherwise take whatever notes you feel that you need to remember the concept. So what we're going to do today, we're going to start by learning how to read the periodic table and how to construct an atom based on it. So the periodic table is all of the pure elements in the universe. There's 90 natural pure elements. The smallest piece of any one of those is called an atom. It has a specific number of protons, electrons, and neutrons, and so we're going to learn how to construct the atoms for several compounds, and then you'll do some more of these in class on Wednesday. So let's start with the simplest element, hydrogen. 74% of the universe is made up of hydrogen. It was the first element at the beginning of the universe, and it is the most prevalent one. It's found mostly in stars, but also in stellar nebula and other places as well. So the setup that you see on your screen is how I will have you diagram an atom as we do this. And we're doing the basic Bohr model of the atom. It's going to have this nice circular orbitals and a certain number of protons and neutrons in the nucleus. So as you see, the nucleus there in green is a rectangle. I use a rectangle rather than a circle for the nucleus so that it's not confused with one of the orbitals. And that's where you're going to put your protons and neutrons. Generally, we'll just write protons, certain number, neutrons, certain number, rather than drawing a lot of little plus circles and equal circles to represent those, because that gets a little cumbersome after you get past a certain number on the periodic table. Over on the left, you see the scoreboard, and we're just going to keep track of what we have. How many protons, how many electrons, how many neutrons, how many orbitals, and how many electrons in the outer orbital. Remember, those are called valence electrons, and those are that's really where the action is in chemistry, is with those valence electrons. Okay. Over on the right, you see the representation for hydrogen, the entry that you would see on a periodic table. The atomic number is the number 1 on the top. The atomic symbol is the H, the name of the element, hydrogen, and then the average atomic mass for hydrogen atoms is 1.01. Okay, so the first, the hydrogen has an atomic number of 1. So if it is electrically neutral, and we assume that it is for all of these exercises, it must have 1 proton and 1 electron, a positive charge, a negative charge. Okay, so what we're going to do is we are going to look at that number, and we're going to go ahead and fill in our scoreboard with a 1 and a 1 for protons and electrons. Okay, now we're ready for neutrons. And this one is this one requires a little bit of a calculation to figure out how many neutrons. Okay, so what we're going to do is, well, we're first going to place our protons in there, or our 1 proton in there, and our 1 electron. We're going to place that off to the side until we have our orbitals set up. So we'll just stick the electron off to the side for now. Okay. All right, next, we're going to figure out how many neutrons the hydrogen atom has. Well, look at the number down there, 1.01. That's called the atomic mass. We're going to round that off to the nearest whole number, the nearest integer. And when we do that, we then refer to it as the mass number. And so we take that and we change that to a 1. Remember what that mass number tells us, or atomic mass. It tells us not only the mass, how much that atom weighs in atomic mass units, but it tells us how many total protons and neutrons it has. If each proton and each neutron has a mass of 1 atomic mass unit, and the hydrogen has a mass of 1 atomic mass unit, then it must have exactly 1 proton and neutron combined. Well, it's got to be the proton, okay? There's no neutrons here. There's just that 1 proton. And so we do a simple little subtraction problem. So the atomic mass tells us the total number of protons and neutrons added together. We can use this to figure out how many neutrons there are. So we're just going to do a little calculation. The atomic mass, really I should say the mass number to be more correct, is protons and neutrons, and we saw that that number is 1. We just rounded it off. Okay, we know that the atomic number, the one at the top, is the number of protons, the one being pointed at there. And that number is 1 as well. So to figure out the number of neutrons, we simply subtract the atomic mass or mass number from the atomic number, and that's going to give us the number of neutrons, and in this case, it's 0. okay? If I tell you you have a bag of apples and oranges, but I don't tell you how many there are, I just tell you there's a total of one in that bag, and I don't tell you whether it's an apple or an orange, but then I tell you that it's an apple, you know that that one thing's got to be an apple, okay? So that's what we're doing here. All right, so over on our scoreboard, we go ahead and fill in the number of neutrons, and that is going to be 0, and we're ready to move on and figure out the number of orbitals. Now, as you look, you should have your periodic table right there in front of you, and if you look at it, hydrogen and helium are in the first row of the periodic table. This is a very important point to understand. The first row represents the first orbital. The second row, which is really technically called a period, represents the second orbital. The third row or period represents the third orbital, and so on. Since hydrogen and helium are in the first row, that means they each have one orbital. We're really interested in hydrogen though right now, so we're going to go ahead and fill in our scoreboard and put a 1 there. All right, so we're moving right along. Scoreboard's 4/5 of the way full. Now, the column or group that an element is in tells you how many electrons it has in its valence orbital, its outer orbital. And in the case of hydrogen, it's in the very first column or group, so therefore it has 1 electron in its valence orbital. That's called the first group, and so we go ahead and we can finish filling in our scoreboard there. We have a 1, so our scoreboard is completely filled. So now we can diagram our atom, and there it is. You have 1 proton, 1 electron, no neutrons, there's 1 orbital, and that is the valence orbital because it's the only one, and you have 1 electron in the valence orbital, so that's how you diagram a hydrogen atom. Okay, let's move on to the next one on the periodic table. That's helium. So first, helium has an atomic number of 2, so it must have 2 protons. That's what the atomic number tells you, and that's what defines it as helium. If it doesn't have 2 protons, it's not helium. So this one does, it has 2 protons. So if helium is electrically neutral, it must also have 2 electrons. So we can go ahead and we can fill in our proton and our electron rows on the scoreboard over there on the left. We have 2 and 2 for each of those. All right, and we'll go ahead and place those protons and in there. And we'll put the electrons, again, we'll put the electrons off to the side until we're ready to place them in the orbitals. Okay, so now we move on, and now we're ready to figure out how many neutrons. So this is the one that requires the calculation. See if you can remember what the next step is. That next step is to take that atomic mass number and round it to the nearest whole number, which would be 4. So we now call that the mass number. And that tells us the number of protons and neutrons in the atom. Again, each proton and each neutron has an atomic mass of 1. So if helium has an atomic mass of 4 as an atom, that means it must have a total of 4 protons and neutrons together. So now we have to figure out how many of those are neutrons. So what do? We do our little subtraction problem. So the atomic mass or mass number, protons and neutrons, is 4. And we know that 2 of those, because of the atomic number up on the top, that 2 of those are going to be protons. That's what that 2 means. That's how many protons. So if there are 4 protons and neutrons, and 2 of them are protons, then the rest have to be neutrons. And there we go. Again, using my apples and oranges. I give you a bag and I tell you it has 4 apples and oranges in it, but you don't know how many of each. So I then tell you, okay, there's 4 apples and oranges and 2 of them are apples. So now I ask you, then how many have to be oranges? Well, the other 2 have to be oranges. So that's all you're doing here. Okay, so now we can fill in the neutrons section of the scoreboard and move on and figure out orbitals. We'll go ahead and place the neutrons in there first. And there you go. Now your nucleus is full. It has its 2 protons and 2 neutrons, which is what helium has. Okay, now we're ready to figure out number of orbitals. Notice where helium is. Just like hydrogen, it's in the first row. Anything in the first row has 1 orbital. So we can go ahead and fill in the orbitals right there, and there's one orbital. Now we're going to finally finish up with how many valence electrons it has, all right? So you'll notice that helium is the second element in the first period or first row. That means it has 2 valence electrons. So we can go ahead and fill in that section, and now our scoreboard is complete. So now we can go ahead and diagram the helium atom, and there it is. 2 protons, 2 electrons, 2 neutrons. It has 1 orbital. Since it only has one orbital, both of its electrons have to be valence electrons on the outermost orbital, and that's how you do helium. All right, let's move on. Let's do another one. Oh, let's read that. There are 2 elements in the first period row, so the first orbital can hold 2 electrons. Now it's full. Okay, boom. No vacancy. So what that's saying is that you're at the end of the first row in the periodic table. Now for the next element, you'd have to move down to the second row, which means what? It means you're going to have 2 orbitals for everything in the second row. So the first orbital can only hold 2 electrons, and then it's considered to be full, no vacancy. All right, let's move on to something else. We'll skip an element here and we'll go to beryllium, which is number 4 on the periodic table. You can see that there. Its atomic number is 4 and its atomic mass is 9.012. So let's go ahead. See if you can do this one. Pause the video and take a minute or two. See if you can do this one. See if you can start off with how many protons, how many electrons, how many neutrons. See how far you can go and then restart the video and see how you did. So in the meantime, I'm going to go ahead and do this, and we're going to go ahead and do this. See if you did pause the video. Let's see how you did on this, okay? So beryllium has an atomic number of 4, so it has 4 protons and 4 electrons since it's electrically neutral. And we're going to go ahead and place those in our scoreboard right there. And then we're going to move on and figure out the number of neutrons. So the first thing that we have to do, and you'll notice down in the nucleus, rather than draw all those circles with pluses and equal signs, we're just going to put protons 4, and then we'll figure out neutrons, and we'll put that number in there as well. Okay? The electrons are going to be put off to the side, so there's, there they are. There's 4 of them over on the right-hand side. Okay, now we're off to go and figure out how many neutrons. And here we go. How do you do that? Well, first we have to round the atomic mass to the nearest whole number, and again, that's going to be called the mass number, and that becomes 9. So that means we have a total of 9 protons and neutrons in the nucleus. So let's do our calculation to figure out how many of those are neutrons. So now we can now calculate the number of neutrons by subtracting the atomic number from the atomic mass. So the atomic mass or mass number is 9. So we have 9 protons and neutrons. We know that 4 of those are protons because that's the atomic number. So therefore the rest of them have to be neutrons, and that is 5. And so we go ahead and put that in our scoreboard, and we can also go ahead and put that in our nucleus. So now our nucleus is complete. 4 protons, 5 neutrons. Now we're ready to move on to orbitals. So how do we do that? Remember we said that the first row represents 1 orbital, and the second row represents 2 orbitals. So all of those in green that you're seeing going across your screen, those all have a second orbital going around them. Okay, and beryllium is the second element over. So let's go ahead though, first of all, and place our orbitals. Okay, there's the 2 in the scoreboard, and there's orbital number 1. It's the first orbital, and there's orbital number 2. Okay, so here we go. Now, we're going to figure out how many valence electrons. So we now get to place the electrons, okay? So we'll do that even before we figure out the valence electrons. The first orbital gets 2 electrons, and then it's full. So we're going to place them there and there. Now, in some diagrams you'll see in books, those electrons will be spread out. I don't like to do that. I like to put them together to show that they're basically married. They're joined together, and that's significant in chemistry, whether electrons are paired or unpaired, as to whether they can pair up with electrons from other atoms to form chemical bonds. In this case, though, the first orbital is filled. It can't take more than 2 electrons because the first 2 elements, hydrogen and helium in the first row, can only have 2 electrons. And so the first orbital, just remember that, is full when it has 2 electrons. Now, what about the other 2? Well, electrons are like people. If you go into a movie theater and there's 8 seats, somebody will sit in one of the seats, and somebody will come in who they don't know and sit in a seat apart from them. They won't sit right next to them. Then the next person comes in, they try to sit apart from them. Same thing. You sit apart from other people until the seats get so full that you have to sit next to people you don't know. You know, nobody totally likes doing that, but once the theater's full, you realize you're going to have to do that. Well, you're going to see in the next example how that works with electrons too. So we're going to put the first electrons, and we see our no vacancy sign on the first orbital. Okay, we'll move on to the next slide. So now we're going to put our first electron, and that's going to go in the second orbital. Now, why did I put it on the bottom? Why not on the side or on the top? Just purely arbitrary. I could have put it anywhere. I just usually put it on the bottom. What about the second electron? Is it going to go right next to it? No, what I just said is electrons like to spread out. So this guy goes over to that side. So now you have 2 electrons in the first orbital and you have 2 unpaired electrons in the second orbital. Those electrons are capable of pairing up with other electrons. Okay. So you can now answer the question, how many valence electrons, or how many electrons in the valence or outer orbital? Okay, since beryllium has 2 valence electrons because it is the second element in the second period. Okay, so 1, and you see the 2. So in order to know how many valence electrons, you simply count from the left how many elements over is it in its row or period. Beryllium's the second element over from the left in the second row, so it has 2 valence electrons, and so now we can fill in our scoreboard and it is complete. And we also have a complete diagram for beryllium. And that's it for beryllium. Okay? This isn't too hard, is it? It just takes a little practice and you'll be doing this very easily in the next day or so. Okay, now we're going to go on to a little bit bigger element. And that's going to be actually considerably bigger. Look at that. That's silicon. If you find silicon on your periodic table, it's way down in the 3rd row, all right, or 3rd period. So let's go ahead and do the same thing. Again, I would encourage you to pause the video, take a couple minutes, and see if you can do this on your own. See if you can diagram silicon and fill in the scoreboard for silicon. Okay, welcome back. If you did pause the video, and hey, glad you stayed with me, or not glad you stayed with me, I wish you had tried the problem, but let's go ahead and do this together then, okay? So here we go. Silicon has an atomic number of 14, so it has 14 protons and electrons. There's that number right there. So that means we're going to fill in our scoreboard with a 14. Pretty big number. All right. We can also fill in our nucleus with the 14 as well for protons. Now we're ready to go on to neutrons. So what do we have to do first? We have to turn. All right, we're going to put the electrons off to the side, okay, and they're going to little by little come in there, and I'm just going to speed this ahead, so boom, there you go, 14 electrons over there on the side, okay? Now, we're going to do neutrons, so what do we have to do? Take our atomic mass and we're going to round it to the nearest whole number, so 28.09 is going to round up to, or excuse me, round down to 28. So that means we have a total of 28 protons and neutrons. So since we know that, we can go ahead and put that in here. And since we know from our atomic number that 14 of those are protons, then 28 minus 14 gives us 14. That means the rest have to be neutrons. So there's the 14. So that's going to go in our scoreboard, and it's also going to go into our nucleus. And there it is. So now our nucleus is filled with 14 protons and neutrons. Nuclei don't always have the exact same number of protons and neutrons, but the number tends to be for smaller elements pretty close. Remember what neutrons do. Neutrons hold the nucleus together. They help to hold the nucleus together. They have a strong nuclear force without having the repulsion of an electromagnetic force, a positive against positive that's pushing the protons apart. They have no charge, so they don't push the protons apart, but they do have the strong nuclear force to help hold it together. So neutrons stabilize the nucleus. Okay, here we go for orbitals. How many orbitals is silicon going to have? Well, look at your periodic table. What row is it in? Yep, it's in the 3rd row. So that means that silicon is going to have 3 orbitals, and so is everything else you see there in green. All of those are going to have 3 orbitals. Now you notice in the periodic table on your screen, we're skipping that big kind of that valley that goes across the middle of the periodic table. We're just going straight from beryllium to boron and from magnesium to aluminum. We'll get into what those metals are down below in a little bit. In a few lessons. Okay, so here we go. The orbitals are 3, so we're going to go ahead and draw those. There's 1, there's 2, and there's 3. So 3 orbitals. Okay, now we can either figure out our valence orbitals right now. Why don't you see if you can do that? How many valence orbitals does silicon have? I think the slide is going to take us into placing the electrons first, but see if you can figure out without doing it, because many times you want to know the valence orbitals without going through all of this and drawing a whole diagram. You want to just know how many valence electrons, not valence orbitals, how many valence electrons an element has. So silicon, if you look at it in the third row, it's the 4th element from the left. There's sodium, Na, magnesium, Mg. You go across the transition metals, which aren't in the third row, to aluminum, Al, and then 4th is silicon. So it has 4 valence electrons. But the other way you could find that is by placing the electrons. So let's go ahead and do that. So we remember that the first orbital gets 2 electrons and then it's full. No more vacancy in the first orbital. It can only hold 2. So that gets a no vacancy sign. Next, watch how we place these electrons. Again, I arbitrarily start at the bottom. You could start somewhere else. But remember that electrons want to spread themselves out. So we put 1 at the bottom. The next one we're going to put on the left side. The next one on top. The next one on the right. Notice how they're spreading themselves out. And this is very significant that these are unpaired. Now, for the silicon, they're not going to be unpaired for very long because we're going to continue to place electrons. The second orbital can hold 8 electrons. And we're going to discuss why that is and the significance of that. But now the second orbital is also no vacancy. It's full. The one reason you can justify that is there's only 8 elements. There's exactly 8 elements in the second row. And so each one contributes an electron as you get from one element to the next. And that's 8 electrons, fills it up. Now the rest of the electrons go into the third orbital. So here we go, we put 1 there, and again, we want to space them out like that. We want to space them out, and finally, we get 4 electrons in the valence orbital. Those are 4 valence electrons. It's very significant that they're unpaired because that means they can match up with electrons from other atoms to form compounds. We'll learn about that later. So there you go, you have your complete diagram, and we can also fill in our scoreboard now, and it says that there's going to be 4 valence electrons, because as we just said, silicon is the 4th element over from the left, and so that takes care of silicon. Okay, and let's see. This is a repeat, so let's go back there. Okay, so let's talk a little bit about atoms in general. Atoms have a nucleus that's very hard and they have electrons buzzing around. What's a little bit surprising and shocking is how much space there is between the nucleus and the electrons. And the fact is there is an atom is almost all empty space. That means that everything made up of atoms, which is everything in the universe, is mostly empty space. So believe it or not, your body is 99.999% empty space. The desk you're sitting at is 99.9999% empty space. So let's look at this example here at the stadium, which used to be Qualcomm, which used to be a bunch of other things. Let's say we put a nucleus of helium right in the middle above the 50-yard line. Okay. Where would the electrons be? Well, there you can see them up in the upper deck there. They're really not staying there. They're buzzing all around the stadium. They basically would be buzzing all over the interior stadium and well up above the stadium and even down underneath the stadium. But that's how far away they would be from the nucleus. Okay, so most of an atom is empty space. So you might ask, well, if it's empty space, why can't you see through it? That would seem like a logical question. And the answer is, in order to see through something, light has to be able to pass through it. And that amount of space is too small for a light wave to be able to pass through. So if light can't pass through it, you can't see through it. So that would explain that. So just because it's empty space doesn't mean it's big enough for a light wave, which requires a certain amount of space to pass through, to be able to do that. All right. Now we're going to get into some terminology here that you're going to use every day in this class. And you need to really commit to what these things are to memory, okay? Just memorize them. It's not a lot of terms, but these two or three are gonna be very, very common. So what is an isotope? An isotope is an atom of the same element, but with a different number of neutrons. So what you're looking at there is lithium. It has 3 protons. That defines it as lithium. Those two atoms both have 3 protons. That defines them as lithium. Whoops. Let's go back. Sorry about that. Okay, so that defines them as lithium. Okay, but you notice that one of them has 4 neutrons and the other has 3 neutrons. So what effect does that have? Really, it has some effects in chemistry. It makes the 4 neutron atom more massive. It's heavier, but that can have some significance in chemistry that we'll get into later on. But it does have to have 3 protons in order to be lithium. Okay, isotope notation. So there's a notation that's used. Now you'll notice it's different than your periodic table. Instead of the atomic number being on the top and the atomic mass being on the bottom, you write the chemical symbol and then you put the mass number. So it's never a decimal number like the atomic mass is. It's the mass number. That's the rounded number we were using in the last few examples diagramming the atom. It's that mass number. But it is specific to, it's really not a rounded number. It's specific to that atom. So these are both lithium atoms. One of them has a mass number of 6 because it has a total of 6 protons and neutrons. The other one has a mass number of 7 because it has 7 total protons and neutrons. The atomic number stays the same. That indicates that it is lithium because it has exactly 3 protons. It has to have 3 protons, otherwise it's not lithium. So that's the notation you would use for an isotope. Okay. Okay, what's an ion? Ions are actually more important in chemistry than isotopes. An ion of an element is an atom that has a different number of electrons than protons. Okay, so if you look at the element or the atom on the left, it's electrically neutral. It has 3 protons and it has 3 electrons. Okay, we don't care about neutrons in the case of ions. What that means is it has no net positive or negative charge. It is electrically neutral. That's a normal lithium atom. Lithium, as we'll learn in the very near future, has a tendency to lose electrons, so to lose an electron. And so if you look at the lithium on the right, you notice it only has 2 electrons. It still has 3 protons, but only 2 electrons. That means it has a net positive charge. In other words, there's more positives than negatives. So it's a positively charged ion, and there's a special name for that we'll talk about in just a second. Okay, so that would be an ion. An ion has a different number of protons than electrons. What's a cation? So this example that we've just been talking about is a cation. It should be a cation is an atom that has more protons than electrons. In other words, it's a positively charged ion. Okay, you guys ever seen the Cheshire Cat from The Wizard of Oz? There he is. So this dude is a positive cat ion, okay? So just remember the positive cat ion, okay? The smiling cat, he's positive. He's got more positives, more protons than electrons. That's called a cat ion. The other type of ion is called an anion. Okay, and if we look at this, an anion is an atom that has more electrons than protons. So count the number of protons there and you find there's 9 there. Okay, there's 9 protons. That means it must be fluorine. Look at your periodic table. Find the atomic number. 9 is F, fluorine. It has to be fluorine, no matter how many electrons or neutrons it has to be fluorine because it has fluorine because it has 9 protons. So, but count the number of electrons and you'll count that there's 10. So there's 1 more electron than proton. The electrons are negatively charged. So this is an anion is an ion that has a net negative charge. So this fluorine atom is an example of an anion. It has 1 more electron than proton. An anion has a negative charge. So here's your mnemonic for that, your little memory device. This grumpy guy is a negative antion. It's really an anion, but just remember the negative ant, and that'll help you to remember a negative anion. Okay, and ionization energy we'll deal with on a different day, so that's it for today's lecture. I would like you to take some notes, show me that you've watched this and that you've taken some notes, what you feel you need, and we'll work some exercises relating to this video in class, maybe play a little quiz game. Okay, you have a nice day. We'll see you in class tomorrow.